Appropriate greetings, ladies and gentlemen. This is Sean McBride, your graduate teaching assistant, and I'd like to welcome you to Lab 4 Practical Linux Systems Programming with the Process API. We're doing things a little bit differently this lab. We're pre-recording the presentation that I normally give at the start of our synchronous lab section and releasing it to all of you a little bit early along with the GitHub Classroom link. And the aim of doing this is to allow each of you to review these materials before the start of lab, such that we can really hit the ground running when we have our synchronous time together. And we want to do that just to alleviate some of the time pressure and make sure that more students are able to complete all of the learning objectives assigned for each of these labs. So our topics for today are really hand-railing off some of the concepts we've been covering recently in our actual lectures. We're going to be talking about processes and threads, the way that processes and threads and multi-process and multi-threaded applications coordinate threads of execution. We're going to be considering a philosophy introduced by a very fascinating programming language, the Airling programming language, which takes a very strong stance about being multi-process. And I think that that's useful to kind of to highlight some of the trade-offs between processes and threads, and how even though threads and shared memory can have better performance characteristics, sometimes there are other factors that are in play. And so built on the Airling philosophy, we're going to build a component called a process manager that really follows the philosophical underpinnings of Airling's idea of a supervisor. That's their term for essentially a process manager. And I'll get into a little bit more what all these pieces are, because I'm sure they're very new, but I think by the end of the lab, you're going to have built something pretty substantial, which has very practical real-world applications. So I think you're going to enjoy that. So when it comes to processes and threads, there are some significant trade-offs. And I realize that these are new concepts to you, but I want you to go ahead and pause the video and consider some of the questions that I put up on this slide. I'll just take a moment and pause. Okay, so by this point, I hope that you've been able to pause and think about some of the differences between processes and threads. These two alternatives are different in a lot of ways. In particular, processes take quite a bit more time to stand up in an operating system, and that's because a kernel has to stand up an entire virtual address space to be able to start up a process, and that's not necessarily true of a thread. A thread is able to use an existing virtual address space, and basically that core idea of having either a shared virtual address space common to multiple threads or multiple independent threads of execution, each having their own virtual address space, that really impacts a lot of ways that we think about our software systems in terms of isolation and fault tolerance and synchronization and debugging. Because over the next couple of weeks, we're really going to be thinking about things like race conditions and locks, thinking about the dining philosopher's problem and stuff like that. And so we're going to hit on a lot of complex programming things. And to some degree, I think when you hit all this, you're going to start thinking, boy, this computer science stuff is really hard, right? And that's definitely true. And you might be wondering, is there another way? Because clearly, like, we have folks that are programming that haven't been to computer science school before, and they've been doing things like coding boot camps, so they may not necessarily understand all this. How do they kind of get their job done, right? Well, there are certain languages and frameworks and things that make some of this a little bit easier, and I'll bring up a little bit of that. But really, the core difference here when we talk about processes and threads, the thing that we really are talking about is the idea of having either shared memory or multiple threads of execution with their own dedicated virtual address spaces that are communicating via message passing. Okay, well, why would you want to have why would you want to pick one over the other? When's the best for shared memory? So for shared memory, usually it's better if you really predominantly care about performance, because in a shared memory system, your multiple threads of execution can directly access the same virtual address space, and that just means that there's less work doing things like copying. Because when you're message passing, Gabe's gonna discuss this more, you end up having to do multiple copies and invoke system calls. And that just adds a lot of overhead just to move data around. So if you can use shared memory, you get better performance, but the problem is that then you have to coordinate all the threads of execution accessing that shared memory. If you don't get your locks right, or there's some sort of obscure race condition, everything may seem okay, and then maybe you run an application for a week or 2 weeks or something, and then eventually the timing is just right where you hit an obscure race condition that violates an invariant of your system, and you end up with wrecked state. And that causes all of your threads to come crashing down. That sort of really obscure problem tends to not really come up as much in a simpler message passing system, and that's because state ends up having to be serialized into these messages that are copied around, and that enforces a little bit more discipline in the state changes of your system. But with that comes different types of complexity. In particular, now that you have multiple copies of data, how do you keep that in sync? Like, how do you know where the freshest information is, and how do you get those changes to propagate it out across your system? And those sorts of questions are really outside of the realm of operating systems and more in the realm of distributed systems, which is a very important and practical for your career sort of subject matter. So if you have the chance to take distributed systems in the future, I highly, highly encourage it. So we've talked about threads and processes, and we've talked about shared memory versus message passing. I just want to bring up that some of the associations I was mentioning before aren't exactly right, and I have just a couple of counter examples here. So typically when you think multiprocess, you think you're probably not sharing memory, but in fact you can. So the way that you would do that with a multi-process system is that you would map in the same region of memory into each of the virtual address spaces using something like mmap. So go ahead and take a look at the man page for mmap if you have any curiosities about how that works. Another counterexample is you could have a multi-threaded system that uses message passing. It's a little bit more unusual for like the C programming language, but this is something that's often provided by a framework or a language. And some programming languages sort of take this approach and like bake it in as one of their core principles. In particular, a language that people commonly associate with this idea is the Go programming language, which it looks very similar to C, but they've really doubled down on this idea of what they call Go routines, which are really green threads, and Go channels, which are essentially pipes or constructs similar to pipes. And this all runs essentially user space. So everything moves a lot quicker because you just don't have the system calls and things like that of standing up a full operating system process. So I'd like to bring up the Airling philosophy now. Airling is another programming language which takes a very different stance. I mean, in some ways it kind of takes a opposite stance, I guess, from the Go programming language. Let me think about that. No, I mean, they're kind of similar, I guess. But Airling and Go both are really designed around a similar problem, how to make it easier to build highly, highly concurrent systems. Because the traditional shared memory multi-threaded model tends to be quite difficult. So in Airling, one of the central ideas is that everything really is a process, and processes interact with each other by exchanging messages. And if you kind of think about that, there are some implications that come up with how you would write software. And a key difference is really around error handling. Because by making everything a process, you have the opportunity to basically outsource all your error handling from your core application logic into something external. And that external thing might be providing centralized error handling for multiple processes. And that tends, like, another place this idea kind of comes up is the idea of microservices, where you have very simple applications, and they have usually something like a proxy or a service mesh that basically does some of this error recovering and error handling work for it. And that just makes it easier to write new programs because you don't have to have all that boilerplate error handling and defensive coding. So the way that this works then is you have this thing called the supervisor, which is what you outsource all your error handling to. So a worker process does the main work. It calls the different APIs and things. The supervisor process observes the worker. In the terms of the POSIX APIs, probably the supervisor process is the parent process, and it has forked a child and execed some sort of process. And it's basically waiting and observing the status of the children. And then if the worker errs, the supervisor is able to take corrective action. And the supervisor in POSIX is able to do that because of the wait APIs or the wait PID APIs and some of the different signals, like the SIGCHILD signal in particular. So in this context, the supervisor really acts as a process manager. And process managers are used all over the place in industry. One in particular that comes to mind is a process manager that's used with Node.js called Pm2, which I've had some practical experience with. And here's the website for Pm2. This is the sort of thing we're going to be building today. It's the logic for being able to just do the basic process manager functionality is pretty simple, but Pm2 has added on all sorts of nifty visualizations that you can get both in the web and then also in terminal using this cool looking ncurses type thing. And so this is the sort of thing that you're going to be building. And so, if this is something you want to run with and you want to add on data visualization and advanced features, maybe you can start your own company like Key Metrics, which created Pm2. So what does Pm2 do? Well, so Pm2 acts as the supervisor, and we use Pm2 to start a script, usually in the case of Pm2, Node.js. And the script runs on top of a runtime. And basically that script runs, and if it errors out, it sends a special message to Pm2, and Pm2 has a way that you can basically program what the process manager should do. So commonly, if the runtime crashes out, you want the process manager to restart the application. But as I showed off that website, the process manager can also do other things like logging and monitoring and stuff like that as well. So our exercise today is we want to fix Gabe's website. I've grabbed the HTML, CSS, and image from Gabe's website, built a very custom web server using TypeScript, and this web server has an error condition whereby it basically has a hard failure 5% of the time. And so in the request handler, essentially it takes rolls like a 20-sided die, and if a particular number comes up, the entire runtime crashes down. And so you might think, okay, I could probably load the web page 20 times if I'm lucky, I guess. And generally it crashes faster than that because when you're loading web pages, you load the HTML page, and the HTML page cascades out to load the CSS page and the image page and maybe a fav icon. And so when you start getting all these requests, things end up crashing pretty quick. So we're not going to be fixing this web server, right? I mean, this is broken and it's going to stay broken. But our mission today is to be able to build a more resilient user experience with broken pieces. And by using something like a process manager, a reverse proxy, and a worker pool, that's something we can definitely accomplish. So the first objective for your process manager is you want to build something that can fork and exec the web server to run Gabe's website. And in this case, it's going to be running on port 8080. And you're going to be able to then hit that website using your browser. And, eventually you're going to get unlucky, hit that 5% odds, and that web server is going to come crashing down. And so for objective 1, you want to basically have your process manager detect when that occurs and then relaunch or respawn the web server on the same port 8080. I think you can kind of imagine, like, just that alone, like, it definitely makes things a lot more resilient, just being able to relaunch processes. But, occasionally that unlucky request that is looking for an image or a CSS file or whatever that triggers this whole thing to come down, that's going to hit the client as an error. So we're still presenting visible errors, and we can make things a little bit better. And the way we do that is by enhancing the process manager to have a pool of workers. So at this point, we launch and we have 3 different web server processes running in parallel. Each of them are running on different ports. And when any of these crash out, we basically want to be able to fail over to one of the other web servers for that request, because they're all serving the same content, right? So we have essentially a primary and 2 backups, and we can do round robin rotations across all those different servers. The challenge here is that, now that you have 3 different workers, when one of them crashes, the process manager kind of has to know, okay, which one crashed and which IP address is no longer available, because you really want to then respawn that worker with that same IP address, because 2 workers can't bind to the same port. So there's a little bit more state and logic. How are you going to kind of manage that in your process manager? So here's what the architecture of this looks like. We have a proxy running in the front, which is something that I've pre-built for you. We have the Deno scripts, which are our web servers running on each of these different ports. And so the proxy, you can basically point your web browser to port 1337, and then you get round robin to one of these different servers. If one of these fails, the process manager respawns, and the proxy knows if I get an error reaching 8080, go ahead and try to request that same asset from 8081. And then if that one also fails, try 8082. And if that one also fails, go back to 80 and see if that one's restarted. And so what happens here is, by having this worker pool and this proxy, all of the requests are successful as long as one of these web server processes is up at any given time. So that's the way that you're able to basically have strong uptime, even when you have components which potentially have bugs or defects themselves. Some of the relevant POSIX APIs that you're going to be using for this lab are really around the family of fork, exec, and wait. But even though we kind of talk about fork, exec, and wait, there are some variants, which I call friends here. And some of these are more useful than others. And I leave it up to your teams to take a look at the man pages for each of these to kind of figure out what's the most suitable. Additionally, when you get to that second objective and you start spawning several workers, you're going to start having some issues around blocking versus non-blocking. And so hint, 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 consider looking at W no hang and consider how that works into your design. So I'm going to quickly demo. So I currently have a Visual Studio Code window open to our lab. And inside of here, this is the repository that you're all going to be able to clone from GitHub Classroom. I'll just show a couple of things in here. So our makefile has a number of things that can be done. We're able to build our process manager using build. We're able to clean, which I think we've had clean in pretty much every project so far. That's pretty standard. We have web, which runs a single instance of the web server on 8081. This is something that you can run immediately before writing the process manager. And this is something that is going to be supplanted and replaced by your process manager when that's done. We're able to run your process manager when that's complete, and we're able to execute the proxy. Let me show you what these different pieces look like. So if I go make web, I'm able to start the web server. I'm able to open this. Looks like I was unlucky there and it errored on the very first request. Wow. Let me try that again. Okay, there we go. So here's Gabe's website. We were able to request his CSS files and his index. And we can go ahead and refresh this. And looks like we were lucky. We were able to get everything. We can refresh again. And that time we were unlucky. And so now when we're unlucky, we have a message here, Chaos Monkey strikes again, and it crashes out our process. To just briefly show you what that looks like. In web server TS, our logic here for essentially running the Chaos Monkey and causing 5% of our request to fail out is here, right? We're taking a random number between 0 and 19, and if that random number is 0, we crash out. The other thing I want to point out in here is this script takes an argument, which is the port number that we run on. And if we don't provide a port number, the default is 8080. And so going back to the makefile, that's what this argument is right here. Some of the other parts of this command are probably interesting to you. Essentially, to run a deno script, we invoke the deno executable, passing it the run command. We say we want to run web.ts, and these are our permissions for how we run web.ts. We want to give web.ts access to read our file system and access to our network interfaces to be able to bind as a server. And we pass the argument 8081. So that's the web piece here. The second piece is the proxy, which I can execute by running make proxy. And the proxy is up. And if I go ahead and click this with nothing actually running, I will open up and you can see we're just rapidly failing, and it's moving pretty quick, but maybe if I scroll up, now it's moving too quick. You would see that it's going 80, 80, 80, 81, 80, 82, and then rolling over. And so the request is hanging here from the client browser. If I want this to be able to succeed, I can load one web server, which by default is on 8081. And even though 8080 and 8082 are not up, this will still roll over and succeed. Right, so now we can see, all these failures here. Finally, one of the web servers was up. So we have, instead of a fail, we have a success. But then the proxy still continues to roll over and get additional failures. So it just has to kind of rotate through enough times, and then it gets all the data back to the client. So you're going to be doing all your work in main.c, which right now is completely unimplemented. But I do have a binary called SPM. The one you build by default is called PM. SPM, that's my initials, so that's my solution here. And I just want to show you what this looks like when you have a fully working process manager. You can run SPM. And you can see here, I've just got some spurious logs here. And the main important thing is HTTP web server running on 8082, 8080, and 8081. And that's important because if I open the proxy script here, those ports are hard-coded. So you have to have 3 different servers bound to those particular ports: localhost 8080, 8081, 8082. And now when I run the proxy and I refresh requests, everything should succeed. If I hit this enough, you're going to notice that some of the different web servers get unlucky and error out. Oh, yeah, so we can see fail, fail, fail. And then over here, we can see particular children returned, and they end up getting relaunched. And so the net result is I can just keep hitting refresh and refresh and refresh. And even though each of these web servers have a 5% error rate, and because they have multiple requests, they end up failing about once every 4th request from the browser, it's undetectable from the user because we are round robining between all of these. And that round robin proxy in front allows the process manager enough time to restart the process. So if I were to run this really hard, probably eventually enough stuff would break that maybe I would have a graphical error. Oh. Kind of glitched there for a second. But generally it's pretty tough. So that's everything. Good luck with the lab. Gabe and I are going to be going around to the small groups once we are synchronous, and we'll be happy to help as much as we can. In the meantime, before the synchronous materials, please pull down the link for this lab. Take a look at all of the scripts here. I definitely don't expect you to understand all this TypeScript. All I really care is that you understand how the process manager that you're going to be building interacts with the proxy and interacts with the web server. So just kind of running these commands and getting a good feel for how those things interact is pretty critical to being successful in this. I'd really suggest running this web command, make web, loading this up in your browser, getting comfortable with how that works, running proxy in a separate tab as I was showing, getting a feel for how that works, and just really having a good mental model for all this before the start of lab. All right, thank you very much and have a good day. Bye.